Yeah, we'll be starting off with complex analysis today. Um, Complex analysis, like it has like fairly diverse number of uses in physics when it comes to you can have the very including the equation, the complex number appears there, and then you have it whenever you want to talk about phase spaces, you have the complex numbers there, and then whenever you're doing analysis, you generally want to include complex functions as well. And we'll see why that is so, why complex analysis is so powerful, first of all. And we'll try to understand like some of the key methods in mathematics that you apply to physics. So it's just going to be pretty simple, right? It's not going to be like anything, of course, right? So analysis at this level is going to deal with only, say, for example, the integrals and the differentiation formulas and how do you deal with and how do you play around with complex numbers essentially. And then we will evaluate like green functions and all of that. But the idea is to just give you an understanding of what are complex functions and why are complex functions used. So of course, like the moment you transcend to say geometry or algebra, the number of ways that complex number or complex function comes in are like extremely subtle, but they're also extremely diverse. It gives you a lot of rich structure. We'll try to understand what this rich structure is. Okay. So first, whenever you start off with complex numbers, how do you represent complex numbers in the sense of like two variables? How do you represent complex numbers?
X plus I y.
Yeah. So essentially, you have some sort of a plane, and then you have a complex number, and this is x, and then this is iy. So this complex number is let's label it G belong to complex. So now how do you represent this point? And when you talk about a function in complex, like in the complex space, first thing that you need to notice is that so you're dealing with a two-dimensional space, and each complex number represents a one-dimensional point in the two-dimensional space. And there is a particular relation to the two-dimensional space in the sense that the moment you square this particular component, you get negative times the real square, like negative times whatever y is. So and this belongs to the real numbers. So negative times like
Y squared, yeah.
So then, so this particular thing, right, like the flipping of signs and this current orthogonality, like those two are the most important tools that we have to understand what complex numbers are. Like, of course, when your functions get more and more complicated, it is more and more complicated to follow through exactly what you're thinking. But it does help significantly if you have like an understanding of what complex functions and like how do these transformation like kind of play role, right? Of course, you can always say that this is if you say I square y square as well, but like you can use that representation as well, but like typically you use complex numbers especially to reduce that I square to and
Solve my
so so now given this, so obviously we know how to write this in terms of x plus iy. It's very simple and Cartesian. Now let's shift to the polar coordinates, right? So then you have your polar coordinates, and then this is theta, this is r in terms of polar coordinates, where r is equal to because you're just dealing with the like the modulus. You're not really looking at the I there. So you just have the magnitude, right? So then you have this is, in other words, this is written as the magnitude of x and magnitude of y square. But so then you have r, and then you have theta is the angle. So you have x. So you can represent it using the sine angle generator. So it should be delta. So r cos theta is equal to x, then r sine theta will be y. So now getting done with that, the most beautiful the undebatedly most beautiful result, simple result in like mathematics comes from the earliest identity, which is essentially e to the power of I plus 1 is equal to 0. I mean, like this is supposed like, so you can see why, right? Like you can see like why this equation itself seems so beautiful. And so first you have 1, then you have pi, you have I, and you have e, all the famous like you know, and you have zeros. So all the famous numbers in math. So so now why does this come to, right? Is because if you understand this, so if you represent, if you talk about the magnitude of r to be 1, so you essentially have like a point confined to a circle of radius 1. Okay, so that's the constraint applicable now, right? So now given this, right, you can represent f in terms of cos theta. So when you write minus 1, how do you write minus 1? To the power of I is equal to, okay, so let's just decompose this a little bit, right? So now we have another thing, which is e to the power of I theta is equal to sine theta plus I cos theta. This is the Euler's formula, and this is the identity of the formula, right? So when you look at this, the angle can be represented in terms of like the x and y axis. So you can represent this in, why do you have this? It's homework. Deriving this equation out is a homework for you guys, because it's fairly simple. You would have done it in like 12th grade, like, you know, even in engineering multiple time, like whatever, with bachelor's multiple time. So deriving, hint would be expand the C in terms of the Taylor series, and then you see like how the I's will keep becoming either I. So first number will be I, and then you will have minus I, minus 1, and then you have so on so on. So when you expand it out, you get e to the power of I theta is equal to sin theta plus I cos theta, which is basically a representation of the circle, and then you have this, right? So minus 1 is equal to e to the power of I pi cos theta. Right? So given this, right, once you have understood what complex numbers are and how they're probably structured, we'll just look at an example in physics. Of course, we won't be going into the full depth of complex analysis there, but we'll just be looking at the examples, and we'll try to figure out where exactly, one of the most famous cases of complex numbers appearing in physics, right? So to talk about this example, first we need to understand what elements of statistical mechanics and quantum mechanics. Okay, we'll deal with your in statistical mechanics, I won't again. I won't be going into the detailed derivations of each of the thing. Most of it is for you to work out. Whatever is gaps are there, for you to work out. But I'll just be giving you the idea, and I need you to feel for the concept, right? So, right. So in statistical mechanics, you have you have this. So given a particular temperature, so you have a probability of finding different particles, right? So given a particular temperature, obviously not all particles are at the same temperature, right? The kinetic energy that corresponds to that particular temperature. But what happens is it is distributed. You have several different distributions, right? So when you talk about the probability of finding a particle with a particular kinetic energy or a particular energy, you try to you set the temperature constant, and then you have several energy states, and you want to find the probability of a particle with a particular energy state. So now, how do you represent the probability? Probability of finding particle with energy state E is given by e to the power of minus E by T. Okay? So you can figure this out, how this works out. And in quantum mechanics, so the probability of a particle moving along a path with the action S. So what happens in classical mechanics is you have S is equal to integral of Lagrangian dt, right? So this is the action, and then once you minimize it, you get the Euler-Lagrange equation. So you insert you know how the principle of variation works, right? So when you say that S is equal to 0, so you insert delta by delta epsilon, so which is the partial derivative with respect to epsilon, except that epsilon takes the value of all the parameters that are the Lagrangian depends on. So you have typically your derivative with respect to your position, and then you have derivative with respect to your momentum. So then you have this to derive the Lagrange equation. So what happens is this is 0, right? So it is minimized. So this is the classical path of the of a body. Now once you go into quantum mechanics, now you don't have a finite constraint to this. You have an expectation, set of expectation values. How you formulate that and how you encode that forms basically the study of whole quantum mechanics. But essentially, you have the action instead of having a strict a strict path. So, for example, if we can represent this, so the solution of this will be a classical path, right? So, it will be some sort of a trajectory. Now, the solution of if you have a quantum, if you have a path integral, as we like to call it, so the solution will be something like, so this is one particle, this is one path, this is one path. So it can take several paths. Typically, for the reasons of analytics, the paths have a certain bound, or else in terms of where what direction your potential is, and you ignore all the other direction more directly. But otherwise mathematically speaking, you have the particles that can take all the possible paths, and then when you integrate it, because of the potential, it gets confined to a particular region. If it is a bound state, if it is an unbound state, you don't have the regions as well, which are more scattered picture. But the idea here is to get the probability of the particle being in its path, you have your probability amplitude, which is you represented by A, right? The probability amplitude of path moving along us. Okay, the particle moving along the path is given by e to the power of I s by h bar. So S is the action. So right. So when you look at it, like you can actually see how these are essentially like either like closed or like some sort of a decaying graphs based on what your energy and your S is. So we won't really like ideally you don't have like any sort of like fixed um, convergence or you don't have anything, right? It's like but we typically fix it to be something that is analytical, right? Something that is confined in to particular value. So for that in quantum mechanics, what you do is you set the probability of a given two stage. So given that I have a room, the probability of the particle being in the room is equal to 1. So like my experiment is confined within the room. So whenever I say like whenever I express it mathematically, obviously I won't be telling the room, or I will just declare the probability amplitudes. I won't be specifying, but like for most like approximations or for most for most calculations, you just assume that the particle is in the room. So you assume those kind of things. So what the subtle point in physics that I'm trying to bring here is that so whenever you're like taking it from math to physics, you're always like defining further approximations. Like I mean, you like physicists are very bad at like defining and specifying everything. So they just like write it off in mathematics. So like in mathematics. So but the thing is, you need to like see what exactly is being confined to it, what exactly is the approximation that you're doing, what is the kind of what is the round off. If you are just aware, maybe you will like embrace the other factors that you might encounter later on, like whenever. So just pointer. So then you have a famous analogy to your statistical mechanics and quantum mechanics is the fact is in two things, right? First is the similarity between the numerator, second is the similarity between the denominators. So just like, so the idea here is that you have your h bar, which is a Planck constant, and you have your temperature, like which is the fixed temperature of the system. So these two are constants of the system. So, but in fact, if you actually notice, your T can change, but your h bar cannot, because it's like, right? So it's something like it's something that is it's a constant of nature, and you can't really play around with it. You can probably create toy models where you have h bar ranging from different attributes and all of that. But as for our consideration, h bar is like a constant and T can change. So just like this is one of the interesting points to just note out, because in what I'm going to talk about. So now we'll start like with defining and deriving some of the like extensions of this theory to understand like some sort of draw some sort of a parallel within this. I think the time is too hard. Yeah. So anyways. Okay, so now how do we get here? So how do we get to this particular expression? right? The idea is you maximize entropy. So we'll look at how we how we derive like this how we get this expression in terms of energy and temperature in statistical mechanics because we understand how to do that, right? And once we do this, we try to draw parallels and try to get something out of this. Of course, again, the missing steps are your homework. So, that's so now, as we know, we go back to the very beginning. So, how is your energy expressed? Is divided into two components: your kinetic energy plus the potential energy. Right? So you have the kinetic energy and potential energy. And so similarly, now you have your free energy of the system. Okay? Your free energy of the system is given by your energy. That is like say your particle is radiating a particular amount of energy, or there is particular energy being put into the system, whatever, however you define it. So energy that goes in and out of the system minus the temperature times the entropy. So actually it is in your thermodynamic formula you have a Gibbs free energy is equal to the energy minus your T theta, right? So this is the thing, this concept, this idea of how of defining a free energy of a system and your energy of a system and separating it from the temperature. So the energy separated from the temperature is very similar to the idea of kinetic energy, energy being composed of kinetic plus potential energy. So now what we need to do here is we need to set, so for example, because it is statistical mechanics, because there are different particles with different energy values, so E is not a constant here, so E is a function, and here similarly according to your E, your S is also a function. Note that this S is different from this S, right? So your E is so based on E, your S is also a function, even though temperature might remain constant, right? So now how do we take this problem and how do we try to minimize it, or what do we try to do with this particular relation? The key here is you know that your entropy is always maximized. For any process to occur, your entropy has to be maximized. So we know that the problem now is not just it's much more simplified, especially with a powerful technique that I'm just about to introduce. But before we go on to that, so I want you to understand how this whole thing works, right? Just a few pointers before that, just to understand how your energy is working. So your energy is so you have energy is different energy states, Ex. So where X belongs to X, which is the collection of all energy states. Actually, it's a collection of all states. It's just a collection of all states because, remember, when you have a basis, you define an arbitrary basis first, and then you project it onto your distance. So your position basis and momentum basis or whatever. So similarly, when your X is just a classification of the different states that are present in the system. So it might be based on your velocities, it might be based on your positions, it might be based on anything. But right now, when you talk about X, but the idea here is X is finite. So you have a band of energy states. That you have each individual energy state represented by the X, and the probability of getting a state of probability of getting a state with energy Ex is given simply is actually P of Ex, which is simply written as Px, which is given by okay. We need to find this out. It is not we need to calculate this. That's the problem, right? So it's just represented by Px. And now the average value of energy is, can anybody guess?
Like sum of all these things.
Yeah.
Summation over all the probabilities.
So summation of Px
into the energy.
into the so you have summation of x belong to okay. So given that, given we have this, now there is another tricky definition of entropy, which actually is it right? Is it like the triple before the kind of problem? It's like you can derive the notion, the probability, the notion of entropy using, as you know, your Lagrange multipliers, and then you have to go a little bit into other things in order to be able to define your entropy as entropy of the system. There is no individual entropy of a state. It's entropy is like a collective thing. So you have the entropy of a system, and roughly speaking, what idea the entropy gives you is if you have a state of say different energies, and you have your x. That's all the states are. So when you have your distribution here, so you can have some distribution like this, you can have some distribution like this, you can have some distribution like this. So you can have several distributions, right? So based on the kind of graph that you get, you can choose your entropy. So it gives you an idea about what kind of distribution is that. Actually, there's a lot of math involved in it, a lot of crazy math, because so you have this definition of entropy as randomness also coming in, right? And then so how widely your information is distributed is something that comes in. But at the same time, when you have something that is wide enough but it follows some sort of a pattern, it seems to be organized, it seems to be ordered. So then you have like further iteration to just like calculate, figure out what entropy is. Going into entropy is it's very fascinating study on its own. And but for our purposes, we have our entropy defined as summation ln logarithm of P of x into P of x. So you have this is the definition of entropy, right? So now how do we, the idea, right? So once you have these two things, what we need to do is we need to minimize this problem. So you have your free energy, okay? So your free energy is equal to E minus dS, and this notion has to be minimized to find the maximum value of x. Because so now once you do this, once you write this whole thing down, we'll briefly look into it. Because although it is not exactly complex analysis, it involves one more very important method in data physics called the method of the Lagrange multiplier. So we'll use the we'll try to use the Lagrange multipliers to solve this particular minimization problem, and then we'll just go back to simplify. I mean, I'm not erasing this. I'll just have this on board. Yeah, so. Right. So one. So coming back, just keeping this in mind. Okay. Keeping this in mind. We have another simple mathematical problem presented for us. That is, if you have a function is equal to, let me not write it as a function, let me write it as, yeah, this is not the Lagrangian. Do not confuse it with the Lagrangian, but we just write it as L is equal to F plus G. Okay? So now we need to minimize this problem. We need to minimize this thing to find the maximum value of G. So we know so how we do this, right? We have this idea that to find the maximum value, you need to have first of all you need to have the derivative of the gradient of this whole function to be 0 for anything to be minimized. So for any maximum condition to be evaluated, you need the gradient to be 0 or like the partial derivative or the derivative or anything. So when you the number of variables, so when you do that, so your gradient of L is equal to 0. That means your gradient of F plus lambda G is equal to 0.
If you're looking to minimize L by maximizing G, shouldn't it be minus? Or is my
no, we're just taking the gradient of L.
No, right. So if you're looking to find, if you're maximizing G to minimize L, then shouldn't it be minus?
No, we'll come to that later. So right now we are just so given this, so we just have like some extreme or like some sort of like saddle points of your L.
Okay.
Okay. So you have saddle points. So it means it might be a maxima, it might be a minima, it might be neither, it might just be something. Right? It might be like just some place where the derivative of L is 0. So it's just a kernel of 0. So once you have this, I mean a kernel of L. So once you have this thing, gradient introduced, of course, like gradient with respect to, so the gradient is defined by, and so you have your partial derivative with respect to X, and you have your partial derivative with respect to Y, and you get a matrix out of that. Right? That's your gradient. So now, in order to do this thing, right? So you have two conditions. You have two things that are possible once you do this particular thing, right? So what are the conditions? So first condition is that your tangent. So if you have your G, okay. So your both G. So for example, if you have your functions, okay. And then this is the space function, and this is your x, and then you have your f of x, and then you have your g of x. G. Right? So you have two functions. Now to find the maximum of this plus this, okay? So what you do is you have two conditions. One is both your tangents are the same and at the same point. Okay, so your tangents are parallel to each other. Okay, that's when you have both x or the f also increasing, g also increasing. So given that, so you can find out. So that is one of the conditions, right? And the second condition is that your tangent of g is 0. Okay, and then it will be positive, increasing positively. So your slope at g is 0, is 0, but your slope at x is increasing. So let's just take this. Okay, so your slope at x is increasing. That is another case, right? So this is where you know that you have a maximum value of g, right? So given this, right, given this idea, you have your whole solution represented in such a way that so once you do this, so you have f is equal to lambda g. So you have this equality to bring in the variation of your so when you talk about the slope, the particular slope, and when you consider when the maximum of f can be occurring in place of g, okay, so when you consider that, right, you can find out that your variation. So first you do the whole, like the main variation, then you find out like your individual experiments. So and then you say that both, like this has to be g has to be maximized. So I mean not g. Sorry, I'm just a little mistaken here. I've put the values of this because we are trying to find out the maximum of g given that f is this. So given given a minimum of, like, so once we find out a minimum of f, then we can find out like corresponding maximum of g. So you have the first principle is to find out the maximum of L itself, like all the extremum compounds of L itself. Okay, it gives you several points, right? Where it's like your f plus g is equal to 0. So in some sense where your slopes cancel out each other. And then you have the gradient of each individual thing should be equal, or it should be a multiple of each other. It's a very subtle thing to understand, and it's even subtler to work with mathematically. But so basically what you're telling is like you can like have a class of functions where when your maxima is when your maxima occurs when the tangents are multiples of each other. Right. So to do that, now coming back to the minimization problem of f is equal to t minus ts. So we want to minimize this. So given these two are functions, as we know here. So given these two are functions, we want to minimize the whole free energy. So once you have the principle of minimum free energy, you have introduced something. So like you have lambda here, you introduce a beta. So you say E is equal to beta x, where beta is the beta is given by the Boltzmann, beta is the Boltzmann distribution. Now, given this minimization problem, given you take care or you minimize your free energy, now you have particular, like, so then we have another constraint, which is that the summation of the probabilities of x is equal to 1, like probabilities of all states to have a particular energy value is equal to 1, right? So given these two things, now then you have you arrive at this relation, right? So you arrive at the probability of getting a particular state is with energy E. Once you substitute these values in and once you do the whole minimization process, like it's a little bit of differentiation. Like you need to bring in a little, like you need to know how to differentiate within the summation sign. So essentially, that's the whole trick. I mean, you can probably pick it up. Yeah, just think that your probability of finding an state with energy x, AEX, is given by e to the power of I beta E x by summation of e to the power of exponential I beta E. Right? So we have arrived at
Like
this
there is no
particular-
minus sign on top, there is no minus sign below.
Yeah.
Numerator.
Yeah, there is no minus sign. So you arrive at this expression, right? So the probability of finding a particular energy state is given like this. Once you can actually, I mean, it's very simple. Like you can actually, the only thing that you need to identify, understand, is where beta comes from, and beta comes from this minimization problem. Right? So the whole procedure. So otherwise, it's just simple. Like it's like you have an energy state, and then you have like the summation of all energy states. So essentially that. But then your beta is important because it gives you the shape of the probability distribution, right? As I said, like the entropy gives you like an idea. So to not ignore the beta. So now this same procedure is something that you need to. Sorry, there's no I here.
This is
no I.
minus.
Because there is remember that we will count numbers that are coming from. There's no I here. Okay, so it's just yeah. So it's just beta here by minus. So that's mine. Again. But the idea is, so you have your probability here. Now, moving on to a completely different picture, I know I'm just doing too many, like bringing in too many ideas together at the same point, but like we'll try to see how it makes sense. Okay? So just also, just for a side note, your beta in statistical mechanics is corresponding to the coolness of the system. So it's proportional to, is related to 1 by T. So beta is somewhat related to 1 by T. So which is the inverse of temperature, which is like the coolness of the system. Okay? It's like resistance and conductance. Something like that. Right? It's not direct. It's not the negative, but it's the inverse.
So, what is the intuition for that? Like, how does increase in beta reduce temperature?
It's just
So once you have, yeah, the increase in so
No, like, how do you think about it?
E is equal to beta S. Now beta is, so when you take beta, so when you set E, then you bring in 3 here. So you kind of like, okay.
Right, right.
It's not a direct mistake,
the,
but
the math is fine, but like, how would you think about it? Like you can substitute and you'll get the relation. That's fair enough.
So you can put beta.
Yeah.
So yeah, so you get that. Okay. How do you think about it?
How would you think about it?
Just the inverse of temperature. 1 by T is equal to beta.
Yeah. Like the math is perfectly clear. Because I was just thinking, because my problem stems from not understanding are not picturing what beta is like. What Boltzmann
So
solution.
what you can probably think of it like look at temperature 0, absolute 0. So there your beta will be infinity. So it will be infinite.
It's like
Infinite.
Coolness. And in fact you can write down your like all your equations in thermodynamics in terms of like instead of temperature you can define it as coolness.
Right.
So at 0, at t is equal to 0, you'll have infinite coolness.
Right.
So then you have some sort of correspondence, I would say, between your yes, this thing graph goes something like this, beta and then t to have what makes it t is equal to 0, beta is infinite, and then
Yeah, that I'm clear.
will have some graph, very half a
Right,
graph.
right.
Yeah, something like that. So, given this, now you can try to, it's just like, okay, how do we define temperature? It's almost as philosophical as asking
Right.
how do we define temperature.
Right. But like I have a fair idea of what temperature is. But
Because you're being used to.
Because I'm used to that,
temperature.
but I just
you've
don't
never
have-
measured
yeah.
things in
Yeah.
coolness. So you've never measured how cold a thing is.
Yeah.
So once you start measuring how cold something is, you can probably develop like a sense. So maybe there's just a few lab experiments away from talking about things in terms of the coldness.
Yeah.
So once you start getting familiar with how to write down things in terms of coldness, so for example, and there's only like you have okay, so in terms of heat, right? Like heat flow, that would also be quite interesting because you have the inverse of the process because like the cold, like you can define some cold heat instead of heat, the cold heat.
Right.
There's nothing.
Yeah.
The cold heat travels from
Away from
hotter body to a colder body. Yeah.
Right.
Yeah.
No. Wait.
No, cold is
Cold heat travels that
Cold
way.
is
So it's like cold heat is emitted from a hotter body. Oh, absorbed by a hotter
Absorbed by a
body.
hotter
Cold
body.
heat is absorbed by a body.
Yeah.
And it's okay. Nice way of logic happening here. But yeah, so we can probably try to define things in terms of coolness as well. But conventionally, it is of course going to be reinventing the language because once we have the notion of a temperature, you like reinventing and like talking about certain things unless there are very specific reasons to talk about this coldness. Like I mean, it's like heating.
Yeah, yeah.
So yeah. So given that, right, once you get done with this, so now let's just take a brief look at quantum mechanics, right? So in quantum mechanics, what happens is there are the probability amplitude of a path with action S is given by exponential of I A of S of S. So instead of S, we'll just put some gamma here because there are too many S's otherwise. Okay, so just to avoid confusion, we'll put gamma by at 1. So by summation of summation of I A gamma yes by
By
to have integral d
BH.
gamma. So since gamma is more continuous, that is not exerted. The action itself is continuous. So you have
It's still by h, right? It's still by h bar in the denominator.
by the So this is the action, right? The average, so the expectation, like the probability of finding a particle with a particular action. It's not the probability amplitude yet, but it's this, right? So now once you have this, so what happens is, so you can define, like you have P here, S here, you can define something called as a entropy is equal to minus summation of any guess? Draw diagram.
Maybe ln A, this ln of, it will just be instead of px, it will be A gamma here.
You can actually derive some interesting relations out of this. So when you try to take the, so how do we do this? When you try to take so when you try to take A as alpha, so the expectation value of the amplitude of a process, like expectation amplitude of a process is alpha, A is equal to alpha. Then you have so the other condition is the summation of all amplitudes is 1. So summation of all probabilities, not amplitude, is equal to 1. So you have these two conditions. So this the term we define as B, right? Okay. So now given this condition, now what you define as the three like, so corresponding to okay, so corresponding to the energy, you have the amplitude, right? So free amplitude of a process, like a free energy of a process. So you have something like Q minus lambda A minus mu P, where A is there, B is there. So when you arrive at this particular minimization problem, and then we will ignore this, okay? But then you find out what we're essentially trying to do is you're trying to find out the equivalent of this thing. We're trying to derive this expression and then trying to find some sort of like relation there, right? So the free action is given by, so when you compute this, your free action is given by A minus I H bar Q. So like your free, A is the action, not the amplitude. A is the action. So A is the action with particular value gamma. Instead of S, we have taken A as to be the action here. Right. So right now, so once you, so in this complicated mesh of relations, once you have this relation is called as a free action. So now, what does free action mean? Like, how do you think about this intuitively? Right? Like you have free energy of the system is the like whatever energy goes in or goes out of the system minus the temperature of the system. So like that. So you have the free action of a system is given by your particular action levels. So that is of an individual particle minus the something that is constant. So this is all still vague. It's like very like, I mean it's just still like there's a lot of work to be done, especially with like clearly defining the parallels and like really trying to understand what this quantum entropy is, and you can actually in fact refer to John Bayes article on this whole on entropy in order to get the whole thing. But the idea here is, so the key problem here with quantum mechanics is your analogies here, right, of minus E to correspond to I A. Right? So this particular thing, so when you're complexifying a variable, it looks like you're complexifying, it looks like you're complexifying P to get IA. You're like taking a real number and making it purely complex to get a completely different thing. So what is happening here? So because generally when you think about quantum mechanics, you do eventually end up with a classical picture of quantum mechanics. So in a sense, you say that hey, you have a particle, and instead of like many particles with many states, you have one particle which can take many states, and then you have the corresponding probabilities and all that. But like when you think classically of the probabilities, it just leads to your statistical mechanics. So now the question that I have is complexification. Okay, so the idea is complexification, instead of thinking about many particles having different energy speeds. Okay, is complexification used to make one particle have many complex amplitudes? So you have one particle having many complex amplitudes, imaginary amplitudes, and then there's only like, so when you sum over the imaginary amplitude, do you like get your real amplitude, like your real like particle, whatever your probability is. So what exactly is the relation? So now notice that like, so when you take, especially here, right, when you write down A, yeah, one of the key problems is you have this expression, right? So your logarithm of a complex number, okay, is, there is one relation, if you recall. So when you represent logarithm of z, okay, so you can write it in terms of the polar coordinate as e to the power phi theta, which is plus I of theta plus 2 pi n. Right? The logarithmic of a complex number is, in fact, it is not one single value. Of a real number, the logarithm is hopefully it's just a light. It's just a light, yeah. Okay, anyway, so the logarithm of a complex number is not single value, it is multi-value. So you have any multiple of 2 pi n which will like give you the same logarithm. So there is no clear way to define this logarithm. Similarly, when you talk about the quantity, right, there is no clear way to define the quantum entropy. Right? So you have like several like zones of entropy which represents the same thing. So you can add to pi to the algorithm, and then you can always get back the same problem. So how does this work? So what is the weird thing that is happening here? There's something that I wanted to answer. So given like your translation between the ideas of your quantum mechanics or quantum mechanical amplitude and your probability amplitude in statistical mechanics, and there's kind of like one body, many body, and that problem, given that particular problem, then you also have this complex space and all of that, which is one way to look at it. But another problem is this, right? So how then do you define entropy? Can you put any restrictions on this? And can you make sure that like you have some sort of common state, and like you only stay in that state, you can't so those are the kind of questions that you probably need to think about. And so the key idea here is like essentially complex numbers make simple things much more complex. If coolness is a complicated thing, just imagine what the coolness of like amplitudes and complex amplitudes and especially what quantity is, right? So so once you translate to the two different pictures, you use the complexification. Actually in other ways, so you have another way to think about this whole problem, right? I just wanted to give you this because this reflects the entirety of all the deeper and more complicated processes in the world, right? So, but otherwise, so you simply have So this is going to be like 5 minutes, right? I'm just going to take 5 minutes and then we'll what's the time?
340.
Okay. 3:40. Okay. Yeah, we'll just take like 10 more minutes and wrap this up. Okay. So one more thing regarding so in other words, so you can represent the average of a process in statistical mechanics is equal to Qj e to the power of E j by KBD. So this is average expectation value of what the process is given by Q. And now then E is the energy of the state, D is the temperature, KB is the Boltzmann constant, and then in kinetic so how do you represent the temperature of gas? So you have Ke is equal to 3 by 2 kBT, and then your velocity of it like a particle is then 3 kBT by they have this kind of relation here, your definition of temperature from velocity of a particle, and then you have your whole thing plugged into the initial temperature. So now what you can do is you can convert your kBT, so you can translate your kBT to the idea of H1 by IT. So you can translate your KVT to h bar by RT. And you just change it. You just change the variables. You just declare that these two things are equal.
What is the small t? The
Time.
time.
So for process to like evolve in certain time, right? You will take it. And now what happens is your complex, the value, expectation value in quantum mechanics for a process to evolve from Q to say another state phi over a certain time t is e to the power I h t by bar, right? Which gives you the expectation like this is the propagator from Q to psi. So this is given by the summation Qj right. So this complex time is called a Wick rotation in your quantum field theory. Like, so what happens when you represent time? So when you have the idea is so you have your dx square is equal to dx square plus dy square plus dz square. I mean, this is d square today. So d square minus d square d, right? So now once you transfer, because this is Euclidean in the sense that it is so you have Pythagoras theorem hold here, right? So this is like everything is just added. You just add different like sides and then you get the hypotenuse, the length of the hypotenuse there. Okay, but once you do this, right? Once you have a negative line, the relativistic because of the relativistic contractions and dilations and all of that. So you have a negative signature here for time. So to make it positive, you replace it by t I down or I t is equal to tau. So then you have like a positive tau is equal to d square of like whatever plus d square t. So this is like completely Euclidean. It's a Euclidean force space. So from like a non-Euclidean space, not this Minkowski space to a Euclidean space, so you have the Wick rotation. So the idea of this is the surprising, right? So the idea of Wick rotation comes in the connection of like quantum mechanics to like statistical mechanics. How exactly, what exactly is happening there is some food for thought. Maybe we will go into this a little later, because this is something that you always want to come back to. But the idea is like you do have like a complexification of time happening here, and you have so all of this, right? So given this, right, given that we see some of the main, most fascinating things in all of physics coming into complex numbers. So and this is DR, and then you have quantum mechanics, and then you have your quantum mechanics, and you have thermodynamics. So all of these three seemingly separate bodies come together as one, like just with the play of like complex numbers. So hopefully, having seen that, let's move on to look at one last one derivation in complex analysis to understand what complex functions are. So we will look at the Cauchy-Riemann theorem. Okay, so the idea of do we take a pause? Do we finish this off or do we take a pause?
And if you want to solve problems, then you will have to pause, right?
We'll finish this off in time. Okay. So now let's take a complex variable. Let's start with the idea of a complex variable. Coming back to the basics. The complex variable is now a complex function is f of z is equal to f of x plus I y, which can be split into two components, which is u of x plus I y plus I v of x plus I y. So this is done. So you know that, like, for example, if you take a square, then y becomes like y transfers itself onto x. So that is the relation, right? That is a beautiful relation. So you have x, sorry, since you don't necessarily have x plus y, so you have x and I and then I u x and I y. So now when you like try to talk about what differentiation means of a function, you essentially know. So first thing here is that you are dealing with a two-dimensional Argand plane, and then you have your function on that. So it's, complex functions are two-dimensional, not curves per se. Okay, so that is the first one of the first things that we need to pay attention to. So because it often gets lost in the value when we deal with like just variables and go into time calculations and all that. So then we have so the idea here is for a complex function, you're so let's try to calculate the differential. Let's try to differentiate f. Okay, so f dash of z is equal to limit as delta tends to 0 of f of z plus delta z minus f of z by delta z. So two things. So how do you so we just have two things, right? So first is you can differentiate with respect to the real part, and you can differentiate with respect to the complex part. So when you differentiate with respect to the real part, what happens? So basically it's like, okay, so when you have a two-dimensional thing, and then you have some sort of a tangent here, right? And you have a tangent here. So the idea is for the function to be differentiable, or if you calculate the tangent from here with respect to x, it should be the same as calculating the tangent with respect to y. Like, I mean, it should like not be the same numerically, but it should be like also negative. So basically this is the same tangent, and you cannot have like two different tangent values here. The idea is you cannot have one tangent here and one tangent here. They should be the same for this to be continuous, right? So when you take that, so now so consider this, like f dash of z and with respect to your u, right? So with respect to, I mean not comma with respect to u with respect to x, right? In the x type. So f y. So when you consider the derivative with respect to f dash of f of g with respect to x, so we just write x and subscript to make it here is equal to, so you have the same thing, right? So then you have when you expand it, you get limit delta x tend to 0 of u plus u of x plus delta x comma I y plus I v of x plus delta x comma y. So you can always write, instead of writing I by v by, you can write it as y as well, minus u of x comma y plus I v of x comma y. So the idea here is that you have taken, instead of taken z plus delta z, you have just specified only x. So because the tangent is one dimensional. So essentially, using that, you can write down the tangent with respect to one variable as the same as the tangent with respect to angle. So when you do this, by delta x, so you end up with du by dx plus I do v by do x. So the same thing when you do it with respect to delta y, y plus delta y. So when you do the same thing with respect to this, then you end up with this particular relation. You end up with minus I do u by do y plus do x do v by do x. So now I will set these two tangents should be equal, right? So because you are calculating the dash c, so it should be equal. Now you have so therefore you end up with the relation when you talk about it. So what's the relation?
You just say
Do u by do x is equal to.
Yeah. So you have do u by do x is equal to I minus I do u by do y, and then you have sorry, wait, yeah, is equal to sorry. The differentiation with respect to x is the same.
So do v by do x.
Do v by do x.
So do v by do y, and then do u by do y is equal to minus do v by do x.
Yeah.
So you put these two together and then you get this. So this is the Cauchy-Riemann condition. So now the idea is, one, you have tangent is one dimensional, you have a function, we have two variables and of two dimensional, plus there is
It
a
should be do y there, right?
Yeah.
Like do v by do y.
Right hand corner.
Yeah, like here. Here.
yes.
Okay.
Right. So you have so you have two dimensions, and then you have a one dimensional tangent vector plus your I the way like when you have like a square and all of that, or like when it cancels out, based on that you have the Cauchy-Riemann equations for a smooth and a continuous and for a differentiable curve.
Right.
So when you talk, when we talk about complex analysis from tomorrow onwards, right, we will be working only with differentiable curves. So, like for your probably we can end this now. We can end the session now.